A supermassive black hole is not just existing at the center of its galaxy but actively killing it by cutting off its star-forming fuel. This astonishing event is happening 11.5 billion light-years away in a galaxy known as Pablo's Galaxy. For the first time, the James Webb Space Telescope has captured this violent cosmic process in action, shedding light on how black holes can shape the fate of their galaxies. In this video, we'll uncover what's happening in this distant galaxy, why it's so important, and what it reveals about the powerful influence of black holes in our universe. The discovery of galactic death by starvation reveals that the James Webb Space Telescope has recently observed a groundbreaking phenomenon in a galaxy known as GS 101578, or Pablo's Galaxy, located approximately 11.5 billion light-years away. This galaxy is being starved to death by its central supermassive black hole. Now, what do we mean by starvation in the cosmic sense? Galaxies need a constant supply of cool, dense gas to form new stars and continue their growth. When this supply is cut off, galaxies enter a quiescent state, effectively halting star formation. Pablo's Galaxy is experiencing precisely this, a process where its black hole is ejecting gas so forcefully that it cannot sustain the birth of new stars. Webb detected this process by observing rapid winds of gas moving away from the center of Pablo's Galaxy at an astounding speed of 2.2 million miles per hour. To put that into perspective, that's about 1,500 times the speed of a top fighter jet. These winds are strong enough to overcome the galaxy's gravitational pull, effectively expelling the very material needed to form stars. This evidence confirms what scientists have long suspected, that supermassive black holes can actively quench their host galaxies by removing star-forming material. Webb's incredible sensitivity allowed it to detect a dense, cooler component of these gas winds, something that previous telescopes have missed. This denser gas is crucial because it blocks light from the galaxy behind it, acting like a cosmic curtain and giving us a more detailed view of the black hole's destructive power. But why is this discovery so important? For decades, astronomers have theorized that supermassive black holes play a critical role in regulating star formation in their host galaxies. However, until now, we lacked concrete observational evidence to support these theories. Webb's observations of Pablo's Galaxy provide the first solid detection of a black hole killing its galaxy by cutting off the gas supply. This discovery is a significant step forward in our understanding of galaxy evolution and the role that black holes play in it. Furthermore, the discovery challenges our assumptions about the nature of early galaxies. Most galaxies in the early universe are bustling with star formation, churning out new stars at a rapid pace. Yet here we have Pablo's Galaxy, which, despite its massive size, 200 billion times the mass of our Sun, has been rendered dead at a time when most galaxies are teeming with activity. The James Webb Space Telescope's observations of Pablo's Galaxy provide a vivid example of a phenomenon known as feedback in astronomy. Feedback occurs when the intense energy released by a black hole, as it pulls in surrounding material such as gas and dust, pushes that material outwards. This ejected gas is crucial for star formation, and when a black hole expels it, the galaxy experiences quenching, effectively stopping the formation of new stars. What makes this observation special is the unexpected aspect of this quenching process. One might assume that such violent ejections of gas would create chaos within the galaxy, causing its stars to become disorganized and potentially altering the galaxy's overall structure. However, in Pablo's Galaxy, the stars continue to move in a well-ordered fashion, suggesting that quenching does not necessarily lead to structural breakdown. This finding challenges previous theoretical models that predicted a more chaotic outcome, providing new insights into the complex interactions between galaxies and their central black holes. This discovery also prompts a reevaluation of what defines a dead galaxy. Traditionally, astronomers have classified a galaxy as dead or quiescent when it no longer forms new stars. However, the case of Pablo's Galaxy shows that star formation can cease even when a galaxy retains its mass and orderly structure. This raises new questions about the criteria for defining a dead galaxy and suggests that there may be more to a galaxy's life cycle than previously thought. These findings open up fascinating avenues for understanding the early universe and prompt us to ask how and why some galaxies manage to grow to such massive sizes only to have their star formation abruptly halted by their central black holes. The research team plans to use the Atacama Large Millimeter/Submillimeter Array in Chile to further investigate Pablo's galaxy. ALMA's ability to detect cold gas and dust will help determine if any cool, dense gas remains and how the supermassive black hole's activity affects its surroundings. These observations aim to provide deeper insights into the interactions between black holes and their host galaxies and how these relationships evolve over time. But Pablo's galaxy isn't the only known example of a black hole killing its galaxy. There are other instances where similar processes have been observed, reinforcing the idea that black holes can be both creators and destroyers in the cosmic theater. One such case is the galaxy Max, which exhibits energy heating the surrounding gas and preventing it from cooling to form new stars. These examples, alongside Pablo's galaxy, suggest that the quenching of galaxies by their central black holes might be a common phenomenon, especially in the early universe. The question then becomes, how frequently does this happen, and what triggers it? By comparing these instances, astronomers hope to identify patterns that could lead to a better understanding of the environmental and internal conditions that make galaxies vulnerable to such dramatic transformations. What makes these findings so special is the direct evidence they provide for a process that was long theorized but never clearly observed. Webb, with its unprecedented sensitivity and resolution, allows us to see the universe in ways we could only imagine before. By capturing these detailed views of distant galaxies, Webb is not only confirming existing theories but also challenging and refining them. The influence of supermassive black holes extends beyond mere star formation. They play a crucial role in the evolution of galaxies and the dynamics of the cosmos. As these black holes consume gas and dust, they not only grow in mass but also emit powerful jets and radiation. These energetic phenomena can interact with surrounding material, creating complex feedback loops that impact galaxy development. One significant aspect of this interaction is the impact of black hole activity on galaxy morphology. For instance, galaxies that host active supermassive black holes often exhibit features such as elongated shapes or peculiar structures that hint at past collisions and mergers. These phenomena can serve as vital clues to understanding the evolutionary history of galaxies. Moreover, the energy released during periods of intense black hole activity can regulate the thermal state of the interstellar medium. This thermal regulation is vital in determining whether gas can cool and condense to form new stars. In some cases, the energy from a black hole may heat surrounding gas to such high temperatures that star formation is inhibited, leading to an aging galaxy that appears dead. Astronomers are also investigating the role of environmental factors in galaxy evolution. Galaxies in dense clusters experience different conditions than those in isolation, affecting how black holes influence star formation. For example, interactions with neighboring galaxies can funnel gas into a black hole, leading to bursts of activity and, consequently, changes in the host galaxy's star formation rate. Recent simulations have provided insights into how black holes might evolve alongside their host galaxies. These simulations suggest that the mass of a black hole is closely tied to the characteristics of the galaxy it resides in, particularly the mass of the stars within that galaxy. This relationship, known as the M-sigma relation, implies that black hole growth is intimately connected to the processes that govern galaxy formation and evolution. The study of active galactic nuclei, AGN, further highlights the complexity of these interactions. AGN are the luminous cores of some galaxies, powered by supermassive black holes accreting material. The light emitted from these regions can outshine all the stars in the host galaxy combined. Understanding AGN helps scientists unravel the intricacies of black hole growth and its consequences for surrounding stellar populations. As new telescopes and observational technologies come online, astronomers are eager to delve deeper into these cosmic mysteries. Upcoming missions aim to observe the early universe, offering glimpses into the conditions under which the first black holes formed and their influence on the nascent galaxies. These investigations will help paint a fuller picture of how black holes shaped the cosmos we see today. Furthermore, studies of gravitational waves, ripples in spacetime caused by the mergers of black holes, offer another avenue of exploration. These waves carry information about black hole masses and their spins, providing data that can confirm or challenge existing models of galaxy evolution. In summary, The intricate relationship between supermassive black holes and their host galaxies encompasses a myriad of processes that influence not just star formation but the overall structure and fate of galaxies across the universe. As research continues to advance, our understanding of these cosmic giants will deepen, revealing even more about the dynamic nature of our universe.